example. Suppose F is a map from Rn to Rn. This map we said it is C1. What's C1 means? C1 means that we know that F is F is determined by its component. Okay, and if all the partial derivative of all the components are continuous, or equivalently, that is, all Fj are C1. I should. That is, using our previous notation, all the Fj belongs to C1 Rn for all j. Okay, this is the meaning of this is what we call F, the map F to be C1. Okay, so if F is C1 and the Jacobian of F at every point is not zero. What this means? This means that this matrix, the Jacobian matrix of F at every point, is invertible. Okay, so this is the second condition. The first condition is smoothness, C1. The second condition is no singularity, which means the Jacobian determinant is not zero, and also assume that as x, the norm of x goes to positive infinity, the norm of fx, because fx is an element in Rn, therefore we need to take the norm to obtain the number. So if this limit is positive infinity, so we have three assumptions. The first is that f is C1. The second is that the Jacobian is not zero everywhere. The third is that the limit, as stated here, is positive infinity. The result is the image of Rn is Rn itself. This means f is surjective. So this is a very classical result, and now you could not prove this result, but you will soon know how to prove this result. Okay, so this is an interesting result. In this example, we use the notion of differentiability and also the Jacobian. Okay, so why this result very remarkable? This result means the meaning of this example is that for any element in Rn, this equation is solvable. Okay, this equation. This is this equation. I write the equation in vector form. Very brief, very elegant. But we can write it in component wise. This equation is exactly this systems of n equations of n variables, n unknown variables. Okay, so this is a system of equation, and all the equations might be nonlinear. This is a system of nonlinear equations. Okay, so in linear algebra, we study systems of linear equations, and the theory is very complete. It can answer every question, whether it has a solution. If the system is solvable, the structure of the solution are all understood. Okay, but for nonlinear equation, this is very difficult. So this example is about when a map is surjective, and this problem is related to the solvability of nonlinear equations. Therefore, it's very important. As we know, solving equation is a central topic in mathematics, and this is not easy. The famous example is the fundamental theorem of algebra, right? Which says that the polynomial px equal to that is a0 xn plus a1 xn minus 1 plus an minus 1 x plus a0 equal to 0. Okay, this is a polynomial. So this polynomial, by the fundamental theorem of algebra, we see that this polynomial, if n is not 0, then there exists a point C in the complex plane such that Pc is 0. So this is to say the equation has a solution. So this is very difficult and a very important theorem in algebra. Therefore, therefore it is called the fundamental theorem. Okay, so even this example, even this equation, except the linear equation, the simplest equation is polynomial equation. Even for this equation, if n is not less than 5, we could not solve this equation analytically. You could not use the coefficients of this equation to write down a formula involving only multiplication and addition and takes roots to obtain a formula for the solution. That is to say, you could not solve this equation analytically. Although theoretically we can convince ourselves, we can prove that the solutions do exist, but you could not write them out. Therefore, the existence of solution for nonlinear equation is very fundamental and very important. Okay, you have to confirm that the equation do exist before you try to find the solution. If you could not find the solution analytically, maybe you can try numerically solution. Okay. So we have talked about the problem of solving equations or systems of equations, and if the equations are linear, then this problem is completely solved in linear algebra. But in many cases, we have to encounter nonlinear equations, such as these systems of nonlinear equations, and also the fundamental theorem about the polynomial equations, which are also nonlinear. Okay, and we just introduce you a classical result about the surjectivity of a map. As we see, solving equation, the problem of solving equation can be converted to the surjectivity of a map. When a map is surjective, and when this map is surjective, this means that for any b in Rn, there exists x such that fx equal to b. So this is the existence of solution. Okay, therefore, surjectivity of map and the other property of map, such as injectivity, are all important. So the above is a classical result on surjectivity of a map. To conclude this lecture, I will be happy to introduce one of our results published in 2018 to you about this problem. This result is proved by an undergraduate student at Xiamen University in Xiamen, whose name is Peng Liu. He is now a graduate student at Peking University. And I will introduce you our result and then compare our result with this classical result. Okay, so suppose F is a map from Rn to Rm. Of course, this map needs to be C1, and there are at most finitely many xi in Rn such that the rank of the Jacobian matrix at this point xi less than m. Different from the classical situation considered in our example. In this example, F is a map from Rn to Rm. The source space and the target space has the same dimension. So the Jacobian metric is a square metric. So we can talk about Jacobian determinant. Here we study the case where the dimension of the source space and the target space could be different. Therefore, in general, the Jacobian matrix is not a square metric. We cannot take a determinant, but we can talk about its rank. So we assume that there are at most finitely many points, so that the rank is not m. The rank is less than m. This is our first assumption. Moreover, we also assume that the image of this map is a closed subset of Rm. So that these are our assumptions. Then we conclude our map is surjective. Okay, this is our result. So compare our result with the above classical result. This is classical. Okay, let's have some comparison. Firstly, our result allow the dimension of the source and the target to be different. So this is one thing. The other thing is that in the classical result, they require for every point the Jacobian determinant is non-negative. This means that for any x, this square matrix is invertible. Invertible means that the rank is n. The rank equal the dimension of the space, the target space. Of course, this is also the source space, because the classical result dealt with the case that they are equal. Okay, so the classical result requires for every point in Rn, the Jacobian matrix, the rank of the Jacobian matrix equal to n. But our result allows the existence of finitely many points, so that the rank is less than n, less than the target space. Okay, so our assumption is weaker than the classical result. This point is crucial to obtain the fundamental theorem of algebra from our result. Okay, this is the the second comparison. Thirdly, the classical result requires that the map is cohesive. Meaning that when x goes to infinity, the norm of fx also goes to positive infinity. So this means this is called cohesive. So the classical result requires that the map f is cohesive. As a consequence of this cohesiveness, you can prove that the image of the map is closed. But in our result, we don't need cohesiveness. We simply assume that the map is closed. So our closeness of the image here is also weaker than the cohesiveness required in the classical result. Therefore, our result improved the classical result greatly. Okay, so our paper has been published in 2018 in American Mathematical Monthly. Okay, so this is the title page of our paper. This paper is suitable for second year undergraduate student. And I hope after we study the inverse function theorem and the implicit function theorem, you can have a look on this paper. Okay.